Garby's lectures last week, so I think most of you are here for Garby's lectures on syzygy. So we start with a smooth curve of genus G, and we take a base point free line bundle L. And we want to study syzygies of the curve C embedded into projective space by the line bundle L. And if you remember from Garby's lectures, the Betti table splits into two components, one of which has to do with this causal groups Kp1 and the other is Kp2. So this talk will focus on the case Kp2. So recall, one says that the line bundle L on the curve C satisfies property NP if Kij CL equals 0 for j at least 2 and I less than equal to p. And here, of course, the causal cohomology groups Kijcl, as you've seen many times last week, is given by the middle cohomology of hi wedge, the ith wedge of h naught L. It's h naught JL, and then you decrease the wedge and increase the multiplicity here. Okay, and here's wedge I plus 1. Okay, and the causal differential was defined last week. I'm not going to repeat it. But this Kij is a middle cohomology in this sequence here. Okay? Okay, so now I make a definition. A line bundle L. So this definition is due to some measure. A line bundle L is said to be P very ample if for all effective divisors D of degree P plus 1, the evaluation map is surjective. So in symbols, for all effective divisors D of degree P plus 1, the evaluation map given by restriction to D is surjective. So this is a very natural positivity condition, and in particular, 0 very ample. It's the same thing as saying base point free. And 1 very ample just means very ample. It's a generalization of this notion to all P. Yeah. Okay. So now I can state the conjecture. So you can also write this condition in terms of there not existing various secants. So this is the cause of the name. This P very ampleness condition can be rewritten in terms of secants to the curve C embedded by L. I won't explain that. I'll just use this definition here. So this. Sorry? Just effective divisors of degree P plus 1. It's just this notation is kind of convenient. Okay, so this is due to Green and Lazarsfeld, 1986. Okay, it says that if you suppose the degree is big enough with respect to P, so we want in this case the bound 2G plus P plus 1 minus the Clifford index. minus 2H1L. Then L is P plus 1 very ample if and only if L satisfies property NP. So as long as the degree is large enough with respect to P plus 1 and natural invariance on the curve, then you can characterize property NP in terms of this positivity condition, the P plus 1 very ampleness. Okay, so first I'll talk about some special cases. Okay, so if you remember, last week Garby talked about this non-vanishing, this Green-Lazarsfeld non-vanishing theorem, and using this it's relatively easy to prove one direction. So the implication to the left is easy. In other words, it is, so it was shown in this paper in 1986 already that if L is not P plus 1 very ample, one can construct a syzygy in Kp2Cl. So in particular, the group Kp2Cl is non-zero. Okay, so if you have that L is not P plus 1 very ample, meaning you have some divisor of degree now P plus 2, such as this evaluation map is not surjective, then you can construct a syzygy. The hard part is to start from syzygy and then to construct a divisor of degree P plus 2, such that this evaluation map is not surjective. Another remark, in the case where the line bundle is the canonical bundle, then it's an easy exercise. I leave to the audience. It's really easy to show that the secant conjecture, in this case, specializes to the famous Green's conjecture that Garby talked about at length, saying that Kp2 C omega C is 0 if and only if P is less than the Clifford index. Okay, so you have to, the only thing you have to do in this exercise is rewrite this P plus 1 very ampleness condition for the canonical bundle. And you find out that it's something related to the gonality, which is related to the Clifford index, and then you end up with this compact statement. So this specializes, this is a more general version of the Green's conjecture. Okay, so the next remark is that in the case where, so for the canonical, H1 is non-zero. It's 1. And in particular, in general, in the case H1 L non-zero, then the statement easily reduces to Green's conjecture. I won't explain this, but it was, I think, observed already in 1989 by Coe and Stillman. That it's fairly easy to reduce this conjecture to the case of the canonical when H1L is non-zero. So really the most interesting case is the case where H1L equals 0, which in some sense is actually the generic case, because for a general line bundle of this degree here, you'll actually have H1L equals 0. Okay, and in this case, it becomes the following, which was proved about 2 years ago, due to myself and Farkas. So this is the generic version. I mean, because this reduces to Green's conjecture, and Green's conjecture is only known for generic curves, there's probably not too much hope right now with current technology of really proving this theorem for every curve and every line bundle. But at least we can prove the generic case. So the statement is that the secant conjecture holds for a general curve C of genus G and the general line bundle L on C. Okay, and I'll just say a couple of words about the proof. So maybe I'll try to leave this. So the proof uses K3 surfaces. The conjecture is known for general curves, for arbitrary curves on K3 surfaces by Voisin and then later work of Raprodu and Farkas. So we can use K3 surfaces to try to get at this problem. And so we need to, so I want to prove this using K3 surfaces. So I need a curve on a K3 surface and a line bundle L on a K3 surface. These two things, this L is not the canonical, so the Picard group has to be at least 2. So you take a K3 surface, and we have the Picard generated by C and L. Let's call it X. Generated by classes C and L. And then for various reasons, so you know what the degree at the intersection of C and L should be by this formula. We know that L should be genus G, which determines the intersection of C with itself. The only thing left to determine is the intersection between C and L. And for various reasons, we set this to be -4. This is forced on us. And then one gets at this result by considering the following standard exact sequence, and using this assumption, this will in fact be a Schrödinger exact sequence. So it's QL minus C. So this should be a Schrödinger exact sequence on the K3 surface X. Then we take this is for all Q. So we have in the middle sections of the line bundle L, so all powers Q. And then we restrict this to C. Okay, so because this self-intersection is -4, in particular, this H1 is always going to be 0, and then you get a Schrödinger exact sequence like this. And then this reduces the statement we want to, oh, sorry, I have to rub this out, to 2 vanishings. So one has this Schrödinger exact sequence here. You can then take causal cohomology of this sequence. And then after taking causal cohomology, the statement reduces to showing Kp2. So we want the causal cohomology of this guy. And you get a natural long exact sequence coming from taking causal cohomology of this short exact sequence. And then it's enough to show that Kp2 of this thing equals 0. And then you get a boundary map, and so you need to show also that Kp minus 1, 3 of this thing is 0. So this thing hasn't been defined, but you can define it easily, and it's like this. And then using the Lefschetz restriction theorem, you can restrict these statements to sections of L, and then this guy is given by this theorem of Voisin, proving Green's conjecture for canonically embedded curves on K3 surfaces. And then to get this vanishing, you have to do a degeneration to the hyperelliptic case. So you degenerate until the divisor D in L is hyperelliptic. This can be done using a K3 surface of Picard rank 3. In this case, you can actually describe this guy here, and you can show that this object here is 0 using hyperelliptic degeneration. Okay. But that's all I'm going to say about this proof. Okay, so this gives you the result. Yeah.
That you can choose L on the surface such that the restriction to the curve is your original L?
I have a K3 surface X with C and with L of the, so that the restriction of it is some L, and I prove it for this restriction. Yeah.
And you can
So I mean, I'm only proving for a general thing. And then, so I mean, once you have vanishing, then you get vanishing on a Zariski open set. It's by semi-continuity. So then, but you can get all degrees in this way. So right now, yeah, this is just for a general line bundle on C. But we can do a bit better in some cases. So I'm going to talk about that now. Yeah. So there is exactly one case. So by one case, I mean one choice of the degree in the genus, where the following two sets both give you virtual divisors, which Gabi talked about. So the set is of pairs of curves C and line bundles L, such that the line bundle fails to be P plus 1 very ample. So you take the set of pairs of curves of genus G and line bundles of degree D such that L is not P plus 1 very ample. And in exactly one case, this will be a divisor, and the same divisor up to a multiplicity as the divisor of curves CL, like this, such that KP2CL is non-zero. So this is a, I don't know what to call this divisor, like a secant divisor, and this is a divisor, like a syzygy divisor, and we know that the result holds for the general. So these two things will be virtual divisors for one case, and then we know that this guy here is an actual divisor. This guy here is known to be a divisor. You compute the classes, and at least as sets, they're equal. Okay, and then this gives you the following statement. So this is something similar to the Hershkovitz-Ramanan proof that Gabi talked about, which gives you, in fact, the Green's conjecture for all curves of odd genus and maximal gonality. So by a morally similar argument, we get the following statement. Okay. So here's a theorem. It says that if C is smooth of odd genus, so genus has to be odd, and the line bundle has to have degree 2G, then you get the statement that Kg minus 3 to of Cl is non-zero precisely when either the Clifford index of C is non-maximal, so in this case the maximal Clifford index is G minus 1 and 2, or L fails to be G minus 1 on 2 very ample. So this is the full statement, in fact, for curves of odd genus and maximal gonality and line bundles of degree 2G. But this is actually a pretty strong statement. So I like to state now one other result that you can get from this theorem. So here this is kind of like the statement for a curve of odd genus and maximal gonality here, because it's kind of only the best result when the Clifford index is maximal. But using this, you can get a result for all possible values of diagonality. Okay, so I have to state the result, I have to recall the linear growth condition of a product. So it was mentioned in the lectures that there is a linear growth condition on the dimension of Brill-Noether loci, which is known to be a sufficient condition for Green's conjecture to hold. This is called the linear growth condition of a product. So C is said to satisfy linear growth if the dimension of the Brill-Noether locus W1 K plus N C is less than or equal to N for all N between 0 and G minus 2K plus 2. So the only important thing you need to know about this condition on the Brill-Noether locus is that it in particular, it's not such a strong condition. So in particular, it lets the curve have arbitrary gonality, and it's satisfied in an open set, which is non-empty in every gonality. And for example, you can check it that it holds on curves on sort of on K3 surfaces with arbitrarily high Picard rank. And this was actually how Proto and Farkas proved Green's conjecture for all curves on any K3 surface, not just on a K3 surface of Picard rank 1. So this is a very nice, this is a very sort of, it turns out to be a very nice and natural condition to put on a curve if you want to study syzygies. And using this, we can get a statement which gets at the secant conjecture, gives you an effective criterion to decide if a curve C in a line bundle L satisfies the secant conjecture, where the curve is allowed to be have arbitrary gonality, and the line bundle L is pretty general. Okay, so this is the following statement. Okay, it's a theorem. Assume C satisfies this linear growth condition, and let's set K to be the gonality of C. So this was used by Garby repeatedly. It's the minimal degree such that there exists a branched cover of C to P1. Okay. Now, so I want to say something else. Right. So I want to study the secant conjecture in the case where we had this inequality. The degree had to be greater than or equal to something. I'm studying for this theorem the extremal case where we have equality here. So rewriting Clifford index using the gonality, because for a curve satisfying linear growth, they're essentially the same thing. Then this means we want to study the case dg plus p minus k plus 3. So then in this extremal case, we have the following result. So firstly, if p is greater than g minus k, or H1 2kc minus L is non-zero, so if either of these two conditions hold, then it's easy, then it's kind of trivial to show that kp2cl is non-zero. Okay, so we don't have to worry about these conditions here. But on the other hand, if we assume firstly these trivial conditions, which we definitely need to have vanishing, that p is less than or equal to g minus k, and that this h1 of 2kc minus L is 0, and then if we impose one more condition, which I'll define in a minute, saying that the secant variety so this is a very natural object, which I'll define in 1 minute. Vg minus p minus 3, g minus p minus 4, 2kc minus L has expected dimension. So this is always some degeneracy locus and always has dimension at least the following number, g minus k minus p minus 1. Then if these two conditions hold, then in fact we have the vanishing kp2cl equals 0. So this gives you effective conditions that you need to, if are satisfied for a line bundle L on a curve which can have arbitrary gonality, and in the case of extremal degree, then we have the vanishing predicted by the secant conjecture. So this is kind of the secant conjecture for curves of for curves satisfying linear growth in the case of this extremal degree. So in the case of equality for the degree, not inequality. Okay, I'll just define what I mean by the secant variety, and then I'll end my talk. So I'll just say that these conditions are satisfied for general curves and general line bundles. It's pretty easy to show that that these are not that the set of curves and line bundles satisfying these conditions is not empty. It's not some trivial thing. It's not. I'm not proving really the empty statement. Yeah. So the secant variety. These are natural things which always come up when you study syzygies. So we take a curve C, take a line bundle with R plus 1 sections. Then, okay, so if it has R plus 1 sections, that's another way of saying that the dimension of the linear system L is R. Then the secant variety VE minus F to L is defined to be all divisors D of degree E, such that the dimension of the space L minus D is 1 higher than you expect. So you'd expect this dimension, this is a divisor of degree E, it's a linear system of dimension R, you'd expect this linear system L minus D to have dimension R minus E, but the secant variety is those divisors such that this dimension is off by F. Okay, so it's a very natural thing to study. Okay, so this is the definition. And the point of the theorem is that you can really verify the secant variety for curves with possibly arbitrary gonality. And arbitrary line bundles, you just have to check some conditions which are relatively natural. Okay, so that's it.